March 30th, 1945. Night sky over Okinawa. Lieutenant Dale Haberman sat in the glass nose of his P-61 Black Widow, watching phosphorescence trail off the propeller blades as his aircraft carved through darkness at 12,000 feet. Behind him, radar operator Robert Graham hunched over the SCR-720 scope, watching green traces paint patterns that represented the invisible geometry of aerial warfare. The intercom crackled. Contact. Bearing 045, range 8 miles, altitude approximately our level. Haberman banked smoothly toward the target. No lights, no visual reference, just trust in the glowing cathode ray tube. Graham was interpreting 3 feet behind his head. The Japanese pilot they were hunting had no idea he was being tracked. No warning receiver in his cockpit could detect the microwave pulses painting his aircraft from 8 miles away. He flew on through the Pacific night, invisible to human eyes but glowing like a beacon on American radar screens. In 4 minutes, he would be dead, killed by technology his nation's scientists had deemed theoretically impossible. The crisis for Japanese night operations had been building since late 1943, when American forces began island hopping across the Pacific. Each captured island became an airbase. Each airbase extended American bomber range deeper into the Japanese defensive perimeter. Japanese fighter pilots, trained primarily for daylight combat against formations of B-29 superfortresses, found themselves increasingly tasked with night interception missions against aircraft they couldn't see until it was too late. The Imperial Japanese Navy Air Service and the Imperial Japanese Army Air Service both attempted night fighter development, but neither service possessed the technological foundation to make it work. Japan had entered the war with radar technology roughly 5 years behind Britain and America. That gap had widened every month since 1941. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. While American engineers refined centimetric radar using cavity magnetrons shared by the British through the Tizard mission, Japanese radar development remained focused on metric wavelengths with limited resolution and range. The Japanese Type II air-to-surface radar, developed for maritime patrol aircraft, could detect ships but lacked the precision for air-to-air combat. The Type III airborne radar, introduced in 1944, represented Japan's most advanced airborne system, but it operated at 1.5-meter wavelength with maximum detection range, barely exceeding 2 miles under ideal conditions. More critically, it couldn't track targets below the aircraft, suffered from severe ground clutter, and required such careful tuning that only specialized technicians could maintain it properly. The Nakajima J-1N Gecko, designated Irving by Allied intelligence, became Japan's primary night fighter by early 1944. A twin-engine aircraft originally designed for long-range reconnaissance, it was hastily modified with oblique-firing cannon in the fuselage for upward attacks against bombers. Some versions received primitive radar, but most crews relied on visual searching, ground-based searchlights, or simply luck. Japanese night fighter pilot, Lieutenant Commander Kozono Yasuna, described the experience in his post-war memoir. "We flew blind, hoping for moonlight or for the B-29 seconds to silhouette themselves against stars. Our radar sets, when they functioned at all, showed vague blurs that might be enemy aircraft or might be mountains. We learned to distrust the equipment and rely on our eyes, which meant we rarely found anything in darkness." The P-61 Black Widow represented everything Japanese night fighters were not. Purpose-built for the role rather than adapted from other designs, it incorporated American radar technology from conception. The Northrop Corporation designed the aircraft around the SCR-720 radar system, creating a night-fighting platform that didn't compromise speed, armament, or range to accommodate electronics. The result was a twin-boom monster spanning 66 feet, powered by 2 Pratt & Whitney R2000, 800 radial engines producing 2,000 horsepower each, capable of 366 miles per hour at 20,000 feet. 4 20mm cannon mounted in the belly, and 4 Browning .50 caliber machine guns in a dorsal turret gave it devastating firepower. But the real weapon was the radar. The SCR-720 operated at 9,145 MHz, approximately 3 centimeters wavelength, giving it resolution Japanese radar couldn't approach. Maximum detection range against a bomber-sized target exceeded 5 miles. Minimum range, the distance where the transmitted pulse overwhelmed the receiver, was down to 300 feet. This meant the radar could track targets from initial detection all the way through the final attack approach, something Japanese systems couldn't achieve. The system used a parabolic dish antenna, approximately 29 inches in diameter, mounted in the P-61's nose, behind a distinctive black-painted radome. The antenna rotated continuously, scanning a cone-shaped pattern ahead of the aircraft. When the operator detected a target, he could switch from search mode to tracking mode, which locked the antenna onto the target and followed it automatically. The radar fed bearing and range information to indicator scopes showing azimuth and elevation. The operator called corrections to the pilot, guiding the fighter through three-dimensional darkness toward an enemy who had no idea he was being hunted. The technological disparity went deeper than specifications. American radar operators trained for months on ground-based simulators before ever entering an aircraft. They learned to distinguish genuine targets from ground returns, clouds, and atmospheric phenomena. They practiced interception geometry until the mathematics became instinctive. By the time an operator reached an operational squadron, he could interpret the green traces on his scope as clearly as a pilot read instruments. Japanese radar operators, by contrast, received minimal training on equipment that barely worked. Technical manuals were incomplete or absent entirely. Spare parts didn't exist. When vacuum tubes burned out, as they frequently did from vibration and tropical humidity, aircraft sat grounded, waiting for replacements that might take weeks to arrive. Maintenance crews learned radar theory through trial and error, often damaging systems further while attempting repairs. The 6th Night Fighter Squadron arrived on Saipan in March 1945, flying the first P-61 seconds assigned to the Central Pacific Theater. Their mission was straightforward: intercept Japanese aircraft, attempting night attacks on American bases and shipping. The Japanese had shifted increasingly to nocturnal operations as daylight missions became suicidal against American fighter cover. Lone raiders would approach at high altitude, drop bombs on airfields or anchored ships, then flee back into darkness before interceptors could reach altitude. These nuisance raids rarely caused significant damage, but they disrupted operations, prevented maintenance crews from working after dark, and forced constant alert status that exhausted personnel. Squadron Commander Major James Ketchum understood his unit's arrival would shock Japanese aircrews accustomed to operating unmolested at night. The Japanese owned the darkness over the Marianas, he wrote in April 1945. Their pilots flew with confidence, born from months of facing no effective opposition after sunset. That was about to change dramatically. The first SCR-720 guided kill occurred on the night of March 8, 1945. Lieutenant Herman Ernst and radar operator Lieutenant Edward Kopsel vectored by ground control toward a radar contact designated as a possible enemy aircraft approaching from the north. Kopsel picked up the target on his scope at 4.2 miles, verified its heading and altitude didn't match any known friendly aircraft, and began calling corrections. Target bearing 010, range 3.8 miles, slightly below us. Ernst adjusted heading and began a gentle descent. The interception took 6 minutes of careful stalking through complete darkness. At 1,000 feet range, Ernst spotted a faint blue glow, engine exhaust flames from a Mitsubishi G4M Betty bomber. He closed to 400 feet, confirmed the distinctive silhouette, and triggered a 2-second burst from his 4 cannon. The Betty exploded, a brief orange fireball that illuminated clouds below before debris tumbled into the ocean. The entire Japanese crew died without knowing an American fighter had been tracking them for the past 6 minutes. Ernst's kill demonstrated the fundamental advantage radar night fighters held over visual hunters. The Japanese crew never had a chance to evade because they never detected the threat. No warning, No defensive maneuvering, just sudden death delivered by an enemy they couldn't see, hear, or detect with any equipment their aircraft carried. Ground-based Japanese radar stations might have tracked the P-61s' approach, but they had no way to communicate warnings to individual aircraft. The Japanese had no airborne radio interception equipment comparable to German Flensburg or Naxos receivers that could detect enemy radar emissions. Japanese pilots flew blind in every sense, unable to see attackers and unable to detect the electronic eyes tracking their movements. The kills mounted through March and April 1945 as more P-61 squadrons deployed across the Pacific. The 418th Night Fighter Squadron operated from Iwo Jima, beginning in April. The 548th Night Fighter Squadron flew from Aishima off Okinawa. Each squadron brought approximately 15 P-61 seconds equipped with SCR-720 radar and crews trained to use it. Japanese losses to night fighters increased dramatically. Bomber crews who survived attacks reported the same phenomenon. Sudden assault from fighters they never saw approaching, often while flying through seemingly empty sky with unlimited visibility. Lieutenant Sakai Saburo, one of Japan's most experienced fighter pilots with over 60 confirmed victories, transitioned to night fighting in early 1945. He described the psychological impact of facing an invisible enemy. In daylight combat, you saw the enemy, and he saw you. Victory or defeat depended on skill, aircraft performance, and courage. But night fighting against the Americans was different. You flew through darkness knowing they could see you, but you couldn't see them. No amount of skill mattered if you didn't know the potic attack was coming. It was like fighting blind against opponents with perfect vision. The SCR-720's effectiveness stemmed from integration with a complete system of ground-controlled interception. Marine Air Warning Squadron 2 operated ground-based radar stations across captured islands, tracking Japanese aircraft from the moment they appeared on screens. Controllers calculated intercepts and vectored P-61 seconds into position using carefully developed radio procedures. Batsman. This is Greenhouse. Vector 090, climb to Angels 12. Bogey, bearing 115, 20 miles, heading southwest, Angels 10. The P-61 crew would turn onto the assigned heading and climb to 12,000 feet, while the ground radar tracked both the fighter and its target. When the aircraft came within the SCR-720's detection range, typically 6 to 8 miles depending on target size and altitude, the ground controller would hand off control. Batsman. Your bogey should be on your nose at 6 miles. Contact when able. The radar operator would scan his scope, locate the target, and begin the final approach phase under his own guidance. This handoff from ground to airborne control was seamless in practice after months of training and standardized procedures. Japanese forces had no equivalent system. Their ground radar stations, where they existed at all, couldn't communicate effectively with airborne fighters. Radar coverage was spotty, maintenance poor, and integration between ground observers and air defense non-existent. Japanese fighters attempting night interception typically relied on orders from ground controllers, who had no real-time tracking, just verbal reports from observers hearing engine sounds or seeing searchlight illuminations. The Americans had built an invisible network across the Pacific that detected, tracked, and killed aircraft with industrial efficiency. The Japanese faced death they couldn't see, couldn't predict, and couldn't counter with any technology or tactics available to them. By April 1945, Japanese night operations over the Marianas and Okinawa had become increasingly desperate. Casualties mounted, while effectiveness plummeted. Bomber crews who survived one mission often refused to fly subsequent night missions, a breakdown in discipline that would have been unthinkable earlier in the war. The invisible enemy was breaking more than aircraft. It was breaking the will of men who faced mathematically certain death without any ability to fight back. The technological foundation that made the SCR-720 possible traced back to British research in the late 1930s. The cavity magnetron, developed at the University of Birmingham in 1940 by John Randall and Harry Boot, revolutionized radar by generating powerful microwave frequencies in a compact package. When British scientists shared this technology with America through the Tizard mission in September 1940, they handed American engineers the key to radar superiority that would dominate the war. MIT's Radiation Laboratory, established in November 1940 specifically to exploit the cavity magnetron, became the center of American radar development. The laboratory grew from a handful of physicists to over 4,000 employees by 1945, producing designs for dozens of radar systems, including the SCR-720. The crash program benefited from America's industrial capacity and scientific infrastructure in ways Japan couldn't match. While American universities graduated thousands of electrical engineers and physicists annually, Japan's technical education system remained small and elite. While American factories mass-produced vacuum tubes, capacitors, and precision components by the millions, Japanese industry struggled with quality control and material shortages. The cavity magnetron itself required manufacturing precision Japan couldn't achieve consistently. The device consisted of a cylindrical copper block with cavities machined to tolerances of thousandths of an inch. Any dimensional error degraded performance significantly. American manufacturers developed specialized tooling and inspection procedures that ensured consistency across thousands of units. Japanese attempts to copy captured cavity magnetrons failed repeatedly due to inability to maintain required tolerances and purity of materials. By 1945, Japan's radar technology lagged at least 5 years behind America's, and the gap was widening. The SCR-720 incorporated refinements learned from earlier airborne intercept radars. The British AI Mark IV, America's SCR-540, and subsequent models had all revealed operational problems that engineers addressed in later designs. The SCR-720 featured improved minimum range, better clutter rejection, more reliable automatic tracking, and ergonomic improvements for operators working in cramped, vibrating cockpits. Each iteration built upon field experience from hundreds of combat missions and thousands of training flights. Japanese radar development had no such feedback loop. Combat experience rarely reached engineers. Operators couldn't provide detailed critiques because they barely understood the equipment they used. Technical problems that American crews would report and see fixed in subsequent modifications simply went unaddressed in Japanese systems, compounding over time into fundamental unreliability. Production numbers revealed the industrial mismatch. The Western Electric Company manufactured approximately 500 SCR-720 systems between 1943 and 1945. Smaller numbers came from other contractors. Total American production likely exceeded 600 units, enough to equip every P-61 built plus provide training sets and spares. Japanese production of the Type 3 airborne radar, their most advanced system, barely reached 100 units total. Most never functioned properly. Many sat in warehouses awaiting installation in aircraft that would never be built due to material shortages. The few that reached operational squadrons broke down quickly and couldn't be repaired. The contrast extended to every component. American vacuum tubes were manufactured by companies like RCA and Sylvania with rigorous quality control. Tubes lasted hundreds of hours between failures. Japanese tubes, handmade in small workshops, failed frequently from poor cathode coatings, internal contamination, and inadequate vacuum. American capacitors used modern dielectrics and maintained stable values. Japanese capacitors drifted in value, with temperature and humidity changes, detuning radar circuits unpredictably. American wiring used proper connectors and shielding. Japanese installations used whatever materials were available, leading to interference and unreliability. Lieutenant Robert Ferguson's kill on the night of April 12, 1945, illustrated how completely radar-dominated night combat. Ferguson and his radar operator, Lieutenant William Lane, were vectored toward a target by ground control at 11:47 p.m. Lane acquired the contact at 7.2 miles, maximum range for the conditions that night. Target bearing 085, range 7 miles, slightly above us, closing slowly. Ferguson adjusted heading and began a gentle climb. The Japanese aircraft, later identified as a Yokosuka P-1Y Francis bomber, continued on its course toward Okinawa, completely unaware of the P-61 climbing toward it through darkness. Lane called continuous updates. Range 5 miles, target steady on course. Range 4 miles, we're closing nicely. Range 3 miles, slightly to starboard now. Ferguson refined his approach, throttling back to match the target speed and avoid overshooting. At 1.2 miles, Lane picked up a second contact. New target, bearing 120, range 4 miles, below us. 2 Japanese aircraft in the area, neither aware of the American night fighter tracking, both simultaneously. Ferguson decided to continue pursuit of the first target. At 800 feet, he spotted the Francis silhouetted against clouds below, moonlight catching the curved surfaces of wings and fuselage. He closed to 400 feet, positioned himself slightly below and behind, and triggered a 3-second burst. 20mm shells walked up the fuselage, detonating in the wing root. The bomber rolled left, trailing fire, and began a steep dive. Ferguson didn't follow. There was a second target waiting. Lane had maintained tracking on the second aircraft throughout the first engagement. Second target now bearing 095, range 3.8 miles. Our altitude. Ferguson turned toward the new heading and began the stalking process again. This interception took only 4 minutes because the Japanese pilot maintained steady course and speed. At 600 feet range, Ferguson identified a Mitsubishi Ki-67 Hiryu, designated Peggy by Allied Intelligence, a twin-engine heavy bomber. He closed to 300 feet and fired a 4-second burst that detonated the bomber's fuel tanks. The aircraft exploded so violently that Ferguson had to bank hard to avoid debris. 2 kills in 14 minutes, guided entirely by radar. Both Japanese crews died without warning, without any chance to defend themselves or even understand what killed them. Ferguson's double kill was not exceptional. Multiple P-61 crews achieved similar results during the Okinawa campaign. The radar gave American night fighters a hunting efficiency that Japanese forces had no counter for. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics of survival had turned completely against Japanese aviators attempting night operations by spring 1945. American P-61 seconds operated with approximately 95% radar reliability. Ground-based tracking provided accurate vectors to within 10 miles of targets. SCR-720 detection range of 5 to 7 miles gave operators ample time to set up intercepts. The combination meant that any Japanese aircraft detected by ground radar faced better than 50% probability of being intercepted and destroyed. These odds made night operations effectively suicidal, yet Japanese forces had no alternative. Daylight missions against American bases in the Marianas and around Okinawa faced massed fighter opposition that guaranteed losses approaching 100%. Night missions at least offered the illusion of concealment, though that illusion died quickly once P-61 seconds arrived in theater. Japanese commanders understood they faced technological inferiority, but lacked any framework for comprehending the magnitude of the gap. Captain Nakajima Tadashi, commanding a night fighter unit operating from Kyushu, wrote in his diary in April 1945, "Our pilots report being attacked by enemy fighters they never saw. Intelligence suggests the Americans have developed radar far superior to ours, but I cannot understand how such technology is possible. How can they detect aircraft at such ranges and track them through darkness? It seems like magic or fantasy, yet our crews die from it every night." This incomprehension pervaded Japanese military thinking. Senior officers trained in traditional warfare concepts couldn't grasp how completely technology had changed combat. They continued issuing orders for night missions, as though darkness still provided concealment, unable to accept that American radar had made night transparent. Younger technical officers who understood electronics tried to explain the situation, but lacked the authority or evidence to overcome institutional skepticism. The result was a death spiral, where Japanese night operations continued despite mounting casualties because leadership couldn't conceptualize the invisible threat, killing their aircrews. The few Japanese pilots who survived encounters with P-61 seconds provided testimony that revealed the psychological impact of facing an invisible enemy. Lieutenant Fujita Iozo described being attacked while flying a Ki-45 Toryu towards Saipan in April 1945. "I was flying straight and level at 8,000 meters when my aircraft suddenly shook from cannon hits. I had seen nothing, heard nothing, received no warning. Fire erupted in the port engine. I dove for the water and managed to escape, but my radar operator was killed by the first burst. I never saw the American fighter that attacked us. To this day, I don't understand how they found us in complete darkness. This sense of helplessness, of being hunted by something invisible and unstoppable, broke combat morale in ways that visual combat never did. Pilots could accept death in daylight combat where they saw enemies and fought back. Being killed by an unseen attacker felt like murder rather than combat, a psychological distinction that eroded the warrior ethos Japanese military culture emphasized. Some pilots refused night missions outright. Others developed psychosomatic symptoms, claiming illness before scheduled flights. Night fighter units experienced disciplinary problems unprecedented earlier in the war, as the reality of facing technological superiority beyond their comprehension destroyed unit cohesion. The SCR-720's capabilities extended beyond simple detection and tracking. The system included several operational modes that gave American crews flexibility. Japanese radar operators couldn't approach. Search mode scanned a cone approximately 60 degrees wide, painting all targets within range on the scope. Tracking mode locked onto a single target and followed it automatically, freeing the operator to monitor other contacts or assist with navigation. The operator could switch between modes instantly, allowing tactics like Ferguson's double kill where he tracked one target while maintaining awareness of a second. The scope presentation used two cathode ray tubes showing complementary information. The azimuth scope displayed a horizontal trace with range markers and a vertical blip indicating target bearing left or right of the aircraft's nose. The elevation scope showed whether the target was above or below the fighter. By correlating both displays, the operator built a three-dimensional picture of target position and could call precise corrections to the pilot. Japanese radar systems, where they functioned at all, presented information in formats that required extensive interpretation. The Type 3 radar used a single oscilloscope showing range and bearing combined in a format that demanded constant mental calculation to extract useful information. Operators needed to manually tune the receiver continuously as aircraft maneuvered, a task that became nearly impossible during combat when vibration, G-forces, and stress degraded motor coordination. The reliability difference was equally stark. SCR-720 systems were designed for operation by trained technicians rather than specialized engineers. Modular construction allowed component-level replacement in the field. If a vacuum tube failed, the radar operator or crew chief could swap in a replacement from spares carried aboard the aircraft and be operational again within minutes. Preventive maintenance procedures developed through operational experience meant most problems were caught and fixed before they caused failures during missions. Japanese radar maintenance required expertise unavailable at squadron level. When systems failed, aircraft sat grounded until specialized technicians could be flown in from rear areas, a process that could take weeks. By 1945, lack of spare parts meant failed components couldn't be replaced at all. Aircraft with radar malfunctions simply had the equipment removed to save weight, returning them to visual-only night fighting with all the limitations that implied. The P-61 itself was designed around the radar rather than having radar adapted to an existing airframe. Northrop's engineers created an aircraft optimized for the radar operator's needs. The crew compartment placed the pilot and radar operator side by side with the gunner behind them, allowing easy communication and coordination. The radar operator had adequate workspace for his scopes, controls, and documentation, even while wearing heavy flight gear. Instruments and controls were logically arranged, with lighting optimized for preserving night vision, while allowing scope observation. Vibration was minimized through careful mounting of electronics and attention to structural resonances that might damage components. Japanese night fighters were adapted from aircraft designed for other purposes. The J-1N Gecko started as a long-range reconnaissance aircraft and was hastily modified when night fighter needs became desperate. Radar installations were afterthoughts, crammed into any available space with inadequate attention to operator ergonomics or equipment protection. Crews worked in cramped positions with poor lighting, inadequate communication, and constant vibration that accelerated equipment failures. The contrast reflected fundamental differences in engineering philosophy. American designers emphasized system integration, where aircraft, radar, weapons, and crew worked as a unified whole. Japanese designers adapted what existed, trying to make incompatible pieces function together through improvisation and operator skill. Major General Curtis LeMay, commanding the 20th Air Force, noted the impact of P-61 operations in his May 1945 assessment. Japanese night raids against our bases in the Marianas have decreased from 20 to 30 per month in January to fewer than 5 per month in April. This reduction is directly attributable to night fighter operations. The psychological impact of radar-equipped fighters appears to exceed the physical destruction they inflict. Japanese aircrews now understand that darkness provides no concealment, and this knowledge has rendered them reluctant to attempt night missions. This psychological dimension was as important as the physical kills. The certain knowledge that American night fighters could find and destroy any aircraft, regardless of darkness, weather, or evasive maneuvers, made night operations appear suicidal. Veteran Japanese pilots who had flown hundreds of missions earlier in the war simply refused to fly into what they correctly perceived as electronic killing zones, where survival depended entirely on luck rather than skill. The radar's limitations were known to American crews but remained unknown to Japanese forces. The SCR-720 struggled with ground clutter when tracking low-altitude targets against terrain backgrounds. Mountains, hills, and even wave patterns could create returns that masked genuine aircraft. The system's minimum, range of 300 feet, meant that if a target somehow closed inside that distance, the radar became useless and crews reverted to visual searching. These weaknesses could have been exploited with proper tactics and intelligence, but Japanese forces never developed either. They didn't understand American radar well enough to identify its limitations and couldn't communicate effective countermeasures to aircrews, even if limitations had been discovered. Some Japanese pilots stumbled onto partial solutions accidentally. Flying very low over water reduced radar detection range by placing the aircraft against the cluttered background of wave returns. Violent evasive maneuvers, when tracer fire revealed an attacker, occasionally allowed escape if the night fighter crew lost visual contact inside minimum radar range. But these survival techniques weren't systematized or taught. They remained individual discoveries that died with pilots who didn't survive subsequent missions. The Americans faced no such knowledge gap. Every P-61 crew was thoroughly briefed on radar capabilities and limitations. Training included realistic scenarios where instructors played the role of targets using known weaknesses to evade detection, forcing operators to develop countermeasures. By the time crews reached operational status, they understood their equipment's strengths and could work around its weaknesses. This professional competence, built on systematic training and institutional knowledge, gave American crews advantages beyond the mere technical superiority of their equipment. The night of May 25, 1945, demonstrated radar night fighting at its most efficient. 10 P-61 seconds from the 548th Night Fighter Squadron flew barrier patrols between Okinawa and Kyushu, positioned to intercept Japanese aircraft attempting raids on American positions. Ground-based radar detected a large formation, estimated at 30-plus aircraft, approaching from the north. Controllers vectored P-61 seconds toward intercepts, spacing the fighters to cover the entire formation. Over the next 2 hours, the American night fighters destroyed 16 Japanese aircraft. Not a single bomber reached Okinawa. The Japanese formation, composed primarily of older aircraft flown by replacement pilots with minimal training, never understood what was destroying them. Individual aircraft simply exploded in the darkness without warning. Survivors who turned back reported overwhelming anti-aircraft fire, not recognizing they were being hunted by fighters their radar couldn't detect. This engagement marked the effective end of organized Japanese night raids on American positions around Okinawa. The loss rate, over 50% for an operation that achieved nothing, made continuation militarily and psychologically impossible. Japanese air commanders shifted remaining resources to daylight kamikaze attacks, where at least pilots could see their targets before dying. The night belonged completely to the Americans, a dominance achieved almost entirely through radar technology. The SCR-720's impact extended beyond night fighting. The same radar technology, with modifications, equipped American bombers for navigation and bombing through overcast. The H-2X radar, derived from British H-2S and built by American manufacturers, allowed B-29 seconds to strike Japanese cities accurately, even when clouds obscured targets visually. Radar altimeters measured height above ground, with precision that conventional barometric instruments couldn't match. Radar beacons guided aircraft to carriers during night operations. Every aspect of American air operations integrated radar at fundamental levels. Japanese forces, by contrast, remained dependent on visual navigation and bombing. Cloud cover that merely inconvenienced American operations rendered Japanese missions impossible. The technological gap manifested in countless small ways that accumulated into overwhelming operational advantages. American aircraft operating at night, in weather, or in conditions that grounded Japanese forces, could maintain pressure continuously. The pace of operations alone, enabled by radar technology, exhausted Japanese defenders who couldn't match it. The few Japanese radar sets that reached operational status revealed design philosophies incompatible with effective use. The Type 3 radar required constant operator attention to maintain tuning as altitude and temperature changed. This manual tuning task alone consumed so much of the operator's concentration that effective target searching became nearly impossible. American radars used automatic frequency control that maintained optimal tuning regardless of environmental changes, freeing operators to focus on tactical employment rather than equipment babysitting. The difference between automation and manual control was the difference between a weapon system and a laboratory curiosity. Japanese radar development was further hampered by inter-service rivalry. The Imperial Japanese Navy and Imperial Japanese Army maintained completely separate research programs, with no information sharing. Both services developed radar systems independently, duplicating effort and competing for scarce resources and technical personnel. Neither service's radar reached acceptable performance, partly because the limited pool of Japanese electronics engineers was split between redundant programs. American radar development, by contrast, benefited from cooperation between services. The Army Air Forces, Navy, and Marine Corps shared research through MIT's Radiation Laboratory and other joint programs. Successful designs were adapted across services rather than reinvented, allowing faster development and better resource utilization. By June 1945, as the war approached its conclusion, the disparity in night air operations had become absolute. American night fighters ranged over Japanese home islands with virtual impunity. Japanese aircraft, attempting night operations, faced systematic destruction. The few remaining experienced pilots refused missions they knew were suicidal. The technological gap that began in 1941 as a manageable disadvantage had widened to an unbridgeable chasm. Japan's inability to develop effective airborne radar was both cause and symptom of the larger industrial and scientific limitations that doomed the nation's war effort. The experience of radar night fighting offered lessons both sides absorbed, though Japan's education came too late to matter. American forces learned that technological superiority, when properly exploited, could achieve dominance disproportionate to numerical advantages. One P-61 with functioning radar was worth more than a dozen conventional fighters groping through darkness. This lesson shaped post-war American military doctrine, emphasizing quality over quantity and technological edge over mass production. Japanese survivors absorbed a different lesson, one tinged with bitterness and recognition of fundamental inadequacy. They learned that traditional military virtues of courage, skill, and determination became irrelevant against enemies possessing overwhelming technological superiority. No amount of bravery could overcome radar that saw through darkness. No piloting skill could evade attacks from enemies impossible to detect. The war taught Japan that modern combat was primarily technological competition, where the side with better science and industry would win regardless of traditional military factors. The legacy of the SCR-720 and the P-61 extended far beyond their wartime service. The principles of airborne intercept radar, pioneered in these systems, became fundamental to all subsequent fighter aircraft. Modern fighters with pulse Doppler radar capable of detecting targets hundreds of miles away descend conceptually from the SCR-720's rotating antenna and automatic tracking. The integration of radar, weapons, and fire control into unified systems traces linearly from the P-61's design philosophy. Every aspect of contemporary air combat depends on electronic systems that began development in the desperate night battles over Britain and the Pacific in the 1940s. For the Japanese pilots who faced SCR-720-equipped P-61 seconds, the experience was one of helpless incomprehension. They flew into darkness, believing it provided concealment, only to discover American radar had made them visible to enemies they couldn't see, couldn't detect, and couldn't fight. The psychological impact of this technological ambush was devastating, breaking the morale of veteran units and revealing the limits of traditional military training against opponents with scientific advantages. Captain Nakajima, who survived the war, reflected decades later on the experience. "We were brave men flying good aircraft, but we were blind fighting enemies with perfect vision. No training prepared us for combat where the enemy saw everything and we saw nothing. It was not war as we understood it, but systematic execution delivered by machines we couldn't comprehend. The Americans didn't defeat us through superior courage or tactics. They defeated us with superior science, and against that, we had no defense." The night hunters of the Pacific Theater, American crews manning P-61 seconds with their SCR-720 radars, wrote the final chapter in aviation's transition from visual combat to electronic warfare. They proved that darkness was no longer concealment, but merely another environmental condition that technology could overcome. The Japanese pilots who died under their guns never understood what killed them because their nation's scientific infrastructure couldn't develop the technology to see what American radar made visible. In that asymmetry lay one of World War II's most decisive yet least celebrated victories: the conquest of night itself through electronics, mathematics, and industrial capacity that turned invisible sky into an ATH, American killing field where Japanese aircraft came to die, hunted by enemies they never saw coming. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.